let's scramble up this Hamiltonian real quick. What we're going to do today, we're going to talk some more about this Hamiltonian operator and how we can start doing things to make it a bit simpler. Then we're going to talk about how do we actually get wave functions for systems through something called the variational principle. And then we're going to talk a little bit about basis sets. So we'll see how far we get. But what we're trying to do right now is to come up with ways to solve. Wow, that was bad. This equation. So when we don't know any of the stuff in there, how do we figure it out? So, all right, we had our Hamiltonian. It had 5 terms in it. Very first term looked like this. What was that for? Yep. Yep, kinetic energy of electrons. How do you know it's kinetic energy? By looking at it. Yep, gradient squared. Whenever you have partial derivatives squared, that usually leads you most of the time when you're talking about Hamiltonians to kinetic energy. And you got some masses in there too that sells it too. Then we got this guy. Okay, what's that for? Yep, kinetic energy of all the nuclei that are in our molecular system. Then we have a double summation. Notice there's a negative sign out front. What's this term for? Yep, because you have electron terms and nuclei terms. And then we have this bit here. What's that for? Yep, so the repulsive force, how do we know it's a repulsive force? Yep, energy raising, positive sign. And then what's our last term? Yep, we got the terms between the nuclei. Okay. All right. We've talked about which ones are repulsive and which ones are attractive. Mathematically, we can just look and see there's a negative sign out front or there's a positive sign out front, so that works. But now the question becomes, this thing is daunting to deal with. Can we think of ways to make this simpler? Good question. How do we make this simpler? Yep. That's where assumptions come in. Some assumptions are valid, some are not. Sometimes you make invalid assumptions just as a first step to build towards a model. So even though your first attempt might not be great, it can still lead to good things. An example of this is Huckel theory. Huckel theory isn't a great approximation, but you can get physical stuff out of it. We're hopefully going to talk about that on Friday, but we'll see. Okay, does anybody know a way we can make this simpler?
We can assume that the nuclei are stationary.
Yeah, that's completely true. We can assume the nuclei are relatively stationary compared to the electrons because their speeds differ so much. So nuclei of molecules move slower, much slower than electrons. So much so it almost appears in the frame of the electrons that the nuclei are stationary. So, therefore, what thing are we going to get rid of out of our Hamiltonian? Yep, this part right here, that kinetic energy. So, is approximated to be 0. The other thing is since the nuclei really aren't moving that much, they're stationary, this term on the end, we can just tack it on as a constant. So this bit can just be constant because the distance between the nuclei will not change much. Oops, capital A, B is a constant. Does anybody know what this approximation is called? There was a recent movie that came out about a scientist and the nuclear bomb. Yeah, this is the Born-Oppenheimer approximation.
I saw the guy's face. So silly.
It's funny because I watched that movie and all my academic great-grandfathers are hanging around in there. Did anybody watch the movie?
Still have to.
Okay. It's a worthwhile one to watch. I personally do not like Oppenheimer. I think this was incredibly low-hanging fruit. Like, I know it was like when things were being developed, I'm just jealous that he got to it first. The other thing is he always said on record that he felt bad about what he did with the atomic bomb, but in reality, he wanted to be famous. He's like Neil deGrasse Tyson, not a real scientist at the end of his career. And I know that probably rubs people wrong too there, but I also dislike him.
Did you prefer Barbie?
I loved Barbie. Margot Robbie, great. She's funny. Now, what was your question, Joe? He claims that he's a scientist when in reality he's like a pop person. He hasn't published anything. The other thing is he's trying to act like Carl Sagan, who was like one of the best scientists ever. Highly intelligent, could speak to the people, and he was still a publishing and active scientist. Where Neil deGrasse Tyson's just sort of like, what's that guy's name?
Bill Nye.
Yeah, Bill Nye. It's like, I mean, they do a great service, I think. They're educating people, but they're not a scientist. They might have been at one point. It's like how, what is it, Anthony Fauci, he's just a pencil pusher. It's okay. It's what happens. Don't talk to Dr. Hilmy about that because I don't know what advice he would have now that he's administrator. But yep, I'll pick on him a little bit though. Okay. Yeah, that's the other thing too. But it was also at a time where Oppenheimer was one of the only people in the United States who was really considering quantum physics to be important. He went to go give a lecture, and I think it was in Dutch. He learned Dutch on the ride over, and he gave his lectures in Dutch. And I can't remember which scientist it was, but I think they were Italian. And they were like, well, he's probably going to talk in English. And then he got there, and the Italian guy didn't know Dutch. So it was pretty funny. Okay, so now I erased all that stuff, which I kind of wish I didn't, but it's gone now. We have the kinetic energy operator, or excuse me, the kinetic energy portion of the operator for the nuclei, which we said is 0. The repulsive interaction between the nuclei we say is a constant. This is going to change our Schrodinger equation. Instead of worrying about all the terms, what are the only terms that are really left over? What do they have to deal with? Not the nuclei, but the electrons. So this changes the Schrodinger equation. Into what's called the electronic missing an R. equation. So it doesn't look very different, but is. This is the electronic Hamiltonian. What is our psi here? The electronic wave function. And what is this energy? The electronic energy. So when eventually we use our computers in class and for daily problems, you're going to be computing electronic energies, and that's what you're really calculating in this case. All right, let's write out our electronic Hamiltonian. So our previous Hamiltonian has lost some terms. We have our first term. Oops, why did I square that? Our second term. Oh, should be A. And our third term.
What's the length? Would it just go away? I know it's constant.
So we sort of pull it out of here. You sometimes tack it in as a constant. So yeah, but you have to, it's dependent on the nuclei. So if you have differing nuclei, they're separated by a distance. There's still some things that can change, but basically you just add in an additional term. So we're just leaving it out. Some people include it in here. Some people add a last portion. It kind of depends on what code you're looking at or how you're thinking about it. For our system, our situation, we're just going to pretend like we leave it alone. Yeah, Joe.
Would it be H hat electron wave function electron is equal to, or electronic is equal to energy electronic wave function electron plus
So you can do that. You can sometimes break this guy apart or add like a potential nuclei. So you can do that, and that's honestly more. Maybe I should do it like that. That is more proper. I'm being a little lazy, and as long as we're cognizant of it, we don't really have to include it. Some purists might get angry with me about that, but it's also like, okay, if I write sodium plus chlorine gets me sodium chloride, there are some people who will be really angry that I don't put the AQ here. And there are some people who know it's implied. I'm assuming we're sophisticated enough to know that it's implied. Does that make sense? Okay. But to be formal, I probably shouldn't. But it's what we're going to do. Okay. Now, next question. We made our approximation simpler. The whole point of making a model simpler is so we can solve it. So my next question is can we solve this? So can we solve this thing? Nope, still can't. Can't solve it exactly with the current mathematics that we have. People are trying. Why can't we solve it exactly? What term's causing all the problems? Nope, double sum isn't the bad one. Yep. Potential energy of the two electrons creates all of the issue, well, most of the issues. We don't have current mathematics to solve this problem. This is known as the many-bodied problem. Yeah, you can do it with even a 2-electron system or a 3-electron system, and what you find is you just get terms that you can't solve for because you have too many unknowns and not enough equations. The other thing is let's just think about the complexity of this situation. So we got electron number 1 here, electron number 2 here, and electron number 3 here. Joe, if I have yellow and blue and white, you can tell those apart. Okay, electron number 1, what's it going to be influenced by in this system?
Electron number 2.
Mm-hmm. Okay, what about 2? What's it influenced by? Okay, what about number 3? Mm-hmm. Okay, oops, I had squiggly lines. Why did I do that? So now, if we're trying to keep track of the coordinate of 1, we also have to know the coordinates of 2 and the coordinates of 3. If we look at 2, we need to know the position, which depends on the position of 1 and the position of 3. The position of 3 depends on what? Mm-hmm. And so you create a problem where they're all dependent on one another. You need to try to guess and check, and you can't do it with what we know how to do it with. There might be some hidden math there. Dr. Hansen, who you know, has never felt comfortable with this, and he thinks there's a way to get around it. If you figure...
There are many ways to get around it.
There are. It's just, does it
It's never
work?
exact.
Yeah, it's never exact. And that's the problem. And some people go, it's exact enough. The way I describe it is how much salmonella do you want in your soup? Like, there's going to be some salmonella in your soup if you have eggs. Doesn't matter. You're like, it's just going to be there. How much can you tolerate?
I have pretty high tolerance, I'm not gonna lie to you.
Yeah. But Joe, that's the problem. And now we start making approximations to combat this. There's some other things too with kinetic energy that I don't really want to touch. And then you have to think back, well, we made another approximation, the Born-Oppenheimer approximation. In some cases, that's not valid, so people get grumpy about that too. For our purposes, this is what we're going to do right now. Okay, so